and then inflate it, and then rigidize it. So in order to do that, there are many methods, but the most conventional one or the most popular one is when we inflate them using nitrogen gas. And there are many issues with that. That is why we are exploring different methods in which we can achieve the same amount of deployment and rigidization without including gas in our structures. So my research is on that. So we are trying to use shape memory alloys. If you would have read that paper, so we are using shape memory alloys, and the interesting property of shape memory alloys is that when we heat them, they change their shape. So we train them in such a manner that they can take a shape that we have trained it to be, or we can just buy shape memory alloys which are trained to contract upon heating. So these shape memory alloys, when we embed them in a structure, so by embedding, I think you understand. So we are putting these shape memory alloys inside a structure, and when we heat them, they are trying to contract, whereas the structure is not able to contract or change its shape. So it causes kind of a morphing in the structure. So utilizing this property, we are trying to put it in, deployable space structures. So this is a very brief way of telling that. Hopefully, in today's talk, I'll be able to cover it.
Okay, ma'am. Thank you, ma'am.
Yeah, no problem.
Good evening, ma'am.
Good evening.
Good evening, ma'am. This is Sukumar.
Hi,
Mm,
Sukumar.
yes, ma'am. Okay, can start. Can we start, ma'am?
Yeah, we can.
Let me give some introduction, ma'am.
Thank you.
Yeah. Casting the world, forging the campus, shaping the universe, and welding the rest. Because you are the machine, we fix the world to fit, and we are mechanical engineers. And greeting everyone. Hello, am I audible?
Yes.
Yeah, yes, ma'am. Sorry. The largest emerging emblematic conclave of mechanical aspirants, ASME NIT Silchar student chapter, embarked upon convincing the students and empowering them to pursue an unabridged core career with renewed interest is now into its next level. As a part of the webinar series MECHATALES, we have witnessed some of the finest, pragmatic, and prominent webinars till date. And we are
Hello.
again with
Hello.
another one.
Am I audible? Hello.
Yes, you are audible, Nitish.
Yes. Today, on the behalf of ASME NIT Silchar chapter, I, Nitesh Kumar Singh, feel very glad to announce that we are having Rupal Srivastava ma'am, PhD candidate at the Department of Mechanical Engineering, Indian Institute of Technology, Kanpur, India. She is currently a member of Smart Materials, Structures and Systems Laboratory and currently working on experimental and numerical studies of the active vibration and shape control of adaptive composites, specifically shape memory alloy reinforced hybrid composites, heavily inclined towards obstetric structures, biomorph and synclastic behavior, and origami-based deployable structures.
Yeah. And she was recently awarded the Skłodowska-Curie Research Fellowship for Postdoctoral Research at Smart Manufacturing Research Center, Confirmed Science Foundation, Ireland, 2021 to 2023. I, Sukuma, feel elated to welcome Srivastava ma'am to share her knowledge and enlighten us.
Thank you so much, Sukumar. That was a beautiful, beautiful introduction. Yes, I am just completing my PhD, and I'll be joining as a postdoctoral fellow in SFI, which is Science Foundation Ireland. And I'm really honored to get to know students from NIT Silchar, one of the best colleges in the country. And hopefully, in today's talk, I'll be able to uh, impart some knowledge on smart materials and smart composites. And also in the latter part of my presentation today, I'll also talk about some smart choices or smart decisions, which is mostly about how to get postdoctoral studies. So I'm not sure the BTech students who are joining, how much beneficial it is going to be for them. But the scholarships that I'm going to talk about, most of them are also available for PhDs. So if after BTech you want to join a direct PhD, you can continue with the talk and you can know more about these fellowships. So the part one will be shape memory alloy reinforced smart composites. I'll be talking about shape memory alloys in detail. And so explaining the title, it just means that these shape memory alloys in the form of wires are being put into composites, thus making them as smart composites. So what are shape memory alloys? These are special class of metallic alloys. And the interesting part of these alloys is that they exist in two different phases, which is martensite phase and austenite phase at two different temperatures. So in most shape memory alloys, the most popular one, which is nickel titanium alloy, it exists in its martensite phase at room temperature, and the martensite phase is a more loosely packed and a soft phase, whereas as we start increasing its temperature, so it reaches its, just a second, I will take this and laser point. So as it reaches its austenite finish temperature, it gets into its austenite phase, which is a more tightly packed and a more stiff phase. So what happens basically in the wire, which we can observe, is that as the temperature increases, the shape and the size of the wire, in this case we are using shape memory alloy wires, they are going to contract. So the ones that we are using are the ones which are going to contract, but there are several other wires which are available in market, which can take a defined shape if you train them to take that defined shape. Now, how the training is done is a more deep process, but to tell about it in just a brief way is that we retrain, we heat it, and then we cool it down, we quench it, and then we reheat it in a certain shape, and then we again quench it. So by doing this process again and again, we are kind of training our shape memory alloys to remember a certain shape. That is why these are called shape memory alloys. So the first time when it was discovered by Boiler in 1965, it was in Naval Ordnance Laboratory, and that is why we call these nickel titanium shape memory alloys as nitinol. So nol is taken from Naval Ordnance Laboratory. And there are, in fact, two interesting properties which are shown by shape memory alloys. The first one is that is shown by this graph, that as we increase the temperature, then we see that there is a thermal shape memory effect. And the other one, when it is in its austenite phase, it shows superelasticity, which just means that it is not going to behave like conventional materials. So as some of you are in your first year, you know the stress-strain relationships that we usually see. We have an yield point, and beyond that, there is a failure. But in case of shape memory alloys, when they are in their austenite phase, they can undergo a large amount of deformation without undergoing plastic deformation. So that is why you see here that in austenite phase, as we are loading them and we are unloading them, these alloys are able to snap back to their original position, and there is no permanent set here. So these are two very interesting properties of shape memory alloys, which can be exploited in many, many ways. And here are some important or major fields in which they are being used. So the first one is shape morphing, where the properties of this shrinking and remembering its shape at a different temperature, it is being utilized. And for aerospace, automobile, and robotics, there are major applications. So this is one of the examples. This is a composite cellular material morphing wing, which was developed by AMES Research Center, which is one of the NASA's research center. And this was developed in 2016. So shape memory alloys are embedded inside these wings. And as the temperature is increased or decreased based on the temperature, the shape memory alloys is shrinking and changing its shape. And now because they're embedded inside a structure, what is happening that the wing is also able to change its shape. What are the benefits of these morphing wings? It's that it is going to help with the control in the drag and lift of the aerospace structure. And also, if we are able to manipulate its shape, thus changing its vibration or natural frequency, we'll be able to avoid failure. So these are the applications in this field. We have it in automobile. So many of you might be aware of the recent Mars rover, which was landed, called Perseverance. So in older Mars rovers, what used to happen was that the tires that we use in these rovers, they're not inflatable tires like we use in our cars or in our bikes. These are made of steel meshes, because no one is going to fix up a puncture in space, on Mars. So these meshes are made of steel, and they are able to undergo huge amount of deformation, but not as much. So that is why the Perseverance rover, which is right now on Mars, the wheels of it are made of shape memory alloy meshes. So as I discussed previously, they show super elasticity as well. So what is happening there is that it can undergo all these huge amount of deformation because of the terrain, because of the uneven terrain of Mars, and still they can regain their original shape and size. So that is another very interesting application of shape memory alloys. Now for robotics, this is a work done by Michael D. Bartlett, and I have put their paper in references here. It's a PNAS paper from 2017. And what they're doing here is that they have a robotic fish, and the caudal fin is embedded. You can see the wires here. So these are embedded with shape memory alloy wires. And as the temperature of these wires changes, they kind of change the shape and size, and they can help in the propelling of these fishes. So this is one of the robotics application. Then there are many. There is autonomous shape control, and then we have biomedical applications. So for stent, we can use them. So if you have an artery which is blocked due to fat, due to unhealthy stuff, so these stents, these nitinol stents, you can see them that they are being used commercially in market actually. So they are put inside. They are transported in a very thin tube. They are put inside the vein, and then they are kind of deployed. So once they're deployed, they push the fat back towards the vein, and the blood flow is then allowed. So this it is able to kind of deploy because it remembers its shape, that it has to take this cylindrical shape, and as soon as the load that is putting it in a compact shape is removed, it takes that cylindrical shape and allows the flow of blood. Then another one is use in dentures, that we use it around our teeth. So usually the common dentures that is available in our market, uh, we have to visit the doctor regularly, the dentist regularly, in order to get it resized or reshaped. But in case of shape memory alloys, if they're already put in the shape of the jaw or the desired shape that the patient should have, once the teeth are in their actual position, then we need not go and get it refixed. It will gradually keep on taking its shape because it remembers that shape, and it will help with the fixing of the teeth. And then there are many, in fact, applications, and then I didn't go much into the structural and the drag reduction and all these applications, but I have put them in short there. Now, coming to why I was motivated to work with shape memory alloys. So when I joined my PhD, in my lab is Dr. Bishak Bhattacharya sir's lab, and he had a ISRO project on inflatable antennas. So there was an inflatable antenna experiment done by NASA in 1996. And what happened in that experiment was that this small 1 meter cube box was sent into space, and these struts were inflated out along with the torus. This torus structure, this ring-like structure, it is also inflated, and this whole structure provided a kind of support for this reflector antenna. So it was a successful experiment, though there were many challenges, but it was a successful experiment in a way that it allowed minimal stored volume. It expanded many folds. It had feather weight, which added to the reduction of the payload cost. And because the packing efficiency was high, it was also helping with the reduction of the deployment cost. And as you know, that ISRO, being a very budget-friendly country, ISRO wanted to kind of redo this experiment in order to make it a success. But there were many challenges with this experiment when it was done by NASA. It was that because these structures are all inflated, you see, so the inflation, first of all, was not controlled. So let's say that one of these struts got inflated first, the other wasn't inflated as much, so the vibration wasn't controllable. Then in space, we also have the effect of shadowing. So what happens that the temperature is so widely different in space that one surface might be hundreds of degrees Celsius, and the other surface will be, which is not facing the sun, will be minus of hundreds of degrees of Celsius. So the inflation was done through a gas, but to put it in that to put that the torus and the struts in the same position, to continue that position, the membranes were embedded or impregnated with UV curable resins. So what happens with these resins is that as sun rays fall on these resins, they cure and they become stiff. So that's how they were made stiff. But because the sun rays are not even everywhere and the heat is not even everywhere, that is why some areas were rigidized first and some were not. So all these things were causing a lot of vibration in this structure. And because there is no air in space, there is no way to damp these vibrations. Another major problem was that because it is all inflated, so if there are space debris kind of pushing with the structure, then there was leakage, and this leakage was leading to degassing. And because of degassing, let's say one of the struts is now completely failed and others are not. So in that case also, the vibration was uncontrollable and it wasn't in a very stabilized state. So to overcome this problem, what we envisioned was, I with my supervisor, was that if we embed shape memory alloy bias in this torus structure, so we are now only focusing on the torus structure because the torus part was what given to IIT Kanpur by ISRO. So if we embedded these torus by shape memory alloy bias, then will we be
Ma'am, hello.
Hello, ma'am. I think your mic is muted. Hello, ma'am.
Ma'am, you are not audible, ma'am.
hello?
Yes, ma'am. You are audible now.
Yeah, was it not audible since the beginning?
No, ma'am.
Yes,
Last
that's
3-4
No, ma'am.
minutes you were not audible.
yes,
In the
Was
previous
this
session.
slide audible?
Yes, ma'am.
Yes, ma'am.
yes, ma'am.
Okay, only this slide wasn't audible. Hello?
Yes, ma'am.
Yes,
Yes, ma'am.
Then
Okay,
this
so I'll
slide.
again start with this slide, okay? Am I audible?
yes, ma'am.
Okay,
Yes, ma'am.
so I think that the last part I will explain it again. So because there are several challenges with the inflation part and also with the rigidization part of this structure, so I with my supervisor, we envisioned to have a structure in which we can remove the requirement of gas and UV curable resins. And in that way, we decided to get introduced with shape memory alloys and to embed these structures with shape memory alloy wires. And using the property of these shape memory alloy wires to bend and take a certain shape, the shape in which they are trained for, we are trying to get this torus like structure. So was whatever I explained the challenges, was that audible? Hello?
Yes, ma'am. Yes,
Okay.
ma'am.
Okay. So I'll come to the next slide. Yes. So for this, we had two different structures in the beginning. Initially, we had these two structures in our mind. So for the first one, it only gave us a unimorph behavior. So the bending was only in one direction. So we had our shape memory wires aligned in 0-degree direction, which is the x-axis, along the longitudinal direction. And as we heat our shape memory wires, they are going to shrink. So as they're going to shrink, because they are at an offset, what is going to happen to the rest of the structure is that the below part is not going to shrink. So it is kind of putting the shape memory wires in a constrained form. And because the shape memory wires are still shrinking because of the heat, the entire structure is going to bend. The entire structure is going to bend along this direction. And in the second structure, because we also wanted a bimorph, and we are talking about a torus-like structure. So in that, we need a very curved like a structure. We do not need just one direction of bending. So we embedded our shape memory wires in 2 layers here and orthogonal to each other. So when this layer shrinks, it is going to bend the structure in one direction. And when this layer shrinks, it is going to bend the structure in other direction. And I didn't mention it before, how we are actuating shape memory wires is by putting these two terminals, these two ends of the wires connected to a DC power supply. So in case of shape memory wires, the only important thing is to increase its temperature. So whatever method we can use a hairdryer, we can use a blower, we can use a hot water supply, we can use whatever. All we need is to increase the temperature so much that it reaches its austenite finish temperature and it starts bending or shrinking or whatever it does. So in our case, we used DC power supply, and by providing it current because of the resistance, the temperature of the wires was increasing and we were able to reach the austenite finish temperature. So then we also thought of these two interesting structures where we had one layer embedded with shape memory alloy wires, and the other layer had honeycomb or reentrant honeycomb ply. So honeycomb, when I say, it is basically like honeycomb, like whatever we know about honeycombs. And it was another ply in the composite. And when we talk about reentrant honeycomb, it just means that these struts, now they are bent inside instead of outside. So if these struts are not bent inside, they'll be like a honeycomb structure, right? So now that they are bent inside, they are reentrant honeycomb structures. And these reentrant honeycomb structures make auxetic structures, which we'll discuss later in this presentation. So in order to define the behavior of these embedded shape memory fibers in composite matrices, Turner, and it's a very famous model. You just Google it, Turner's ECT model, you'll come to know about it. What happens in conventional materials is that we are now studying maybe in first year, second year, we have alpha delta T, right? So that is because of the thermal expansion. So whenever we write our equation, we have sigma is equal to that Hooke's law. We have sigma is equal to E, then we have epsilon, and we have alpha delta T. And we always associate alpha, the thermal coefficient of expansion, with the expansion of the material. But the interesting part with shape memory alloys is that when we increase the temperature, it is shrinking. So it is effective coefficient of thermal expansion, but in this case, it is contraction. So here you can see that when temperature is greater than austenite start, so our material is in its austenite phase, we have this interesting term called sigma R, which is called recovery stress. So this term was given by Turner, and it's the stress which is generated by the shrinking of the wire. So let's say we have a long straight wire, okay, and one end of the wire we are going to fix it, and the other end let's add it to some load. And as we are going to heat the wire is going to shrink. Now, as it shrinks, it is going to take the load that is added on the other end with it. So how much load is it able to take with it? Because not in all cases it is going to take like 10 kgs or 5 kgs. There is going to be a certain amount of load that it is going to take with it. So that load is corresponding to this recovery stress. That was what given by Turner. And then when it is not in its austenite phase, it is the normal equation that we use for our materials whenever there is temperature involved, conventional materials. So then Turner said that our sigma in one direction for the actuator material. So instead of SMA, as I have used in my modeling, he is using A. So whenever you see A for Turner, it is for the SMA layer. So it is going to be, as we are increasing the temperature from initial temperature to the maximum temperature, this is how he envisioned it, where alpha is a function of tau, where tau is a function of temperature, which means that it's a function of temperature. And from this equation, if we compare this equation 1 compared with, let's say, compared with this equation, I haven't termed it, but yeah, comparing equation 1 with this, we get that sigma R is this. So we have a value for our recovery stress, and taking sigma r, here we get a given value for our alpha from this. So whenever we do it experimentally, we are able to figure out sigma r. So there's a method. We just add our wire uh, to a load cell, and then we heat it, and we get the values of load at different temperatures. So we are able to get sigma r at various temperatures, and we are also able to get E at various temperatures because there is temperature controlled UTM machines available. So we are able to get Young's modulus at different temperatures, and that is how we figure out what the alpha would be. So we have this cum-trap's function in MATLAB. So we just calculate the cumulative alpha for each and every temperature. And I'm not going to go into depth how this is achieved, but there is a very interesting book. It's called Agarwal and Rootman. So it is on composites. And that is where they explain how we are getting these tensorial stresses. So we are usually used to look into basic Hooke's law, sigma is equal to E epsilon. Now, why is this compliance matrix coming? It's because we have our structure here, and it has materials all different in all directions, so that it's an orthotropic material. Hooke's law is only applicable to isotropic material. So when the materials are all, the material properties are all different in all directions, so along one it is different, along two it's different, and also along the z direction, that is the thickness, it is different. The equation is somewhat like this. And this part is added because we have SMA bias embedded. So if this part wasn't there, it would have been a normal orthotropic material with no temperature involved. Okay, so what are these Q matrices? I'll just go ahead. These are reduced stiffness matrices, and they are calculated by Halbin's equations and by rule of mixtures. And the elements, which were Q11, Q12, and all, as we saw it previously, so all these elements, these are nothing but your Young's modulus in one direction, your nu12, nu21, Young's modulus in two direction. So these are all very easy to calculate if you have all the material properties at your hand. And how do you calculate E1, E2? It's by EAVA plus EMVM. Now, what is VA and VM? It's the volume fraction of SMA. So how much volume of shape memory alloys do you have in your structure? How much volume of matrix, because they're embedded in some other structure, right? So how much amount of that is there in the structure apart from shape memory alloys? So E is the Young's modulus of shape memory alloys, and EM is the Young's modulus of the matrix in which shape memory alloys are embedded. So similarly, we calculate them for other properties, and for alpha, we also have similar kind of equations. And when we figure out all these properties, we just plug it in these equations, and we have our sigma versus epsilon direct relationship, because now we have our matrices with us. These are called compliance matrices. Okay. So I'm not going into depth, but I'm just putting it out there so you can understand how I'm going to get to my FEM model. Okay. So a little bit about auxetic structures, because I talked about those reentrant structures, and then you were like, what is that? So auxetic structures are very interesting solid structures. Usually in our conventional materials, when we pull our structures in the longitudinal direction, then it is going to shrink along the lateral direction. So if you have, let's say, a rubber band, okay, you are going to stretch it, and you'll see that it will start to get thinner and thinner because it's a conventional material, it's rubber. But with auxetic structures, as you pull it in one direction, it is also going to expand in another direction. So as you are as it is expanding along x-axis, it is also going to expand along y-axis. So they have negative Poisson's ratio. Okay, so here's a small experiment that I did in my lab. Just a second, I'll try to play it. Yeah. So what here we did was that using kirigami, we made these reentrant lattices here, and as we actuated, so we have SMA springs here. So there are SMA wires, then we have SMA springs. In many ways, we can mold our shape memory alloys actually. So we had SMA springs attached to the ends, and as we heated them up, they are going to shrink. So these are shrinking, and as if you see closely, you'll see that as it is increasing in length, it is also increasing in depth. Okay, I'll play it again. See, it is increasing in its breadth also. So these are auxetic structures, and this is just one example of reentrant auxetic structures. There are many more ways in which we can make a structure in such a way that it can show us auxeticity. Now, these are auxetic structures. There are also some auxetic materials which are available. So this property that we see, auxeticity, is because the way the structure is made. But there are some materials also which themselves behave in that manner, that when we pull that material, it is going to expand in other direction also. And these materials are also micro manufactured. So some air bubbles are put inside the material while they are being manufactured, and these air bubbles act as pockets which are responsible for the auxeticity in these structures. So just search about auxetic structures. Just go on YouTube, and they have many applications and many beautiful experiments. Okay. So moving on, these are some applications that I'm going to explain, and they are both done in my lab. So the first one that one of my colleagues did was stiffness control. So these are all honeycomb structures where this angle, this theta, this angle is positive. And when we bend it inside, then it's reentrant. Okay, so this reentrant angle causes auxeticity. So what he did was that on a piece of this strut, he's putting piezoelectric material. I'm not going to get into piezoelectric material as well, but yeah, so piezoelectric material he was putting on top of it. And then he was able to observe that by changing the cell angle from minus to positive. So minus, always remember that it is going to give us auxetic behavior, that is negative Poisson's ratio. And this positive is going to give us normal Poisson's ratio like we see in our conventional materials. So our E1, E2, G12 are all varying as we go from minus 90 to plus 90 here. And this elastic moduli here, do not worry, it's not 10 raised to the power 10, it's non-dimensionalized. So they are taking a ratio of the elastic moduli of this entire structure in E1 direction, or whatever line suggests, and divided by the elastic moduli of the structure, that is the material that it is made of. So it is all non-dimensionalized. So, but still there is symmetry. So how do we see that auxeticity is helping? Because in positive Poisson's ratio at, let's say, 40 degree, there is the same value, and then again at minus 40 degree, the value is same. So how is it beneficial? So the piezoelectric material, when actuated, okay, so when it is a positive voltage, positive negative is just that we are changing the polarity, okay, of the connection of the piezoelectric material, we see that there is a major change in the elastic modulus. So at minus 40, what we are getting, we are not even getting it in our positive range. So when we are able to attach an active material to this structure and actuate this material, which is the piezoelectric material, we are able to change the elastic modulus of the structure from something else to something else based on what the theta is. So this is one application of auxetic structure. So we can control the Young's modulus of the entire structure, okay? The other very interesting work that was done in my lab was vibration control. So was a very interesting work which was published in Scientific Reports, Nature. And in that, what my colleague did was that he had this hourglass structure made of conventional material. He 3D printed it using PLA. And then he had made this another one, which had honeycomb lattices, as you can see here. And then the third one had auxetic lattices, and then he just mixed and matched. It had auxetic, honeycomb, and then conventional honeycomb and conventional auxetic. So just see that if we are going to give some kind of, just a second, some kind of vibration here on the bottom there. So it's a 3D structure, okay? It's an hourglass 3D structure. So if we are going to give some kind of vibration here, will this structure give us some kind of damping so that the plate or whatever we have put on top of it, is it going to give us a different behavior or different displacement? So will this structure be beneficial when we come to the field of vibration control or not? So this is one way. And another way is that if we have several units, repeating units of this structure, which is called metamaterial, then if we are actuating it on one end, will we be able to get a different frequency at another end? So let's say that if it's observed 100 hertz and some displacement on this side, what will be the output displacement? So we calculate the displacement transmissibility, which is nothing but the displacement caused by the given frequency at input divided by output, okay? So what he found was actually very interesting, that when we changed our structure from conventional to the honeycomb and auxetic structures, we were able to change the frequency of the structure. So we are able to get a different frequency for all these different mix and match conditions. And that is how we can also use auxetic structures for vibration control. There are many more applications. There is impact resistance, and then there are many, in fact, applications of auxetic structures. I've not covered them all, but these are two very interesting, and they are from my lab, so I thought of sharing. So these auxetic structures are the one that I'm going to use in my composites. These are just basic equations of how the E1, E2, nu1, 2, all these equations, all these material properties are calculated for a honeycomb structure. And in order to calculate them for auxetic structure or reentrant honeycomb structure, all we have to do is that change this theta to minus theta, because our struts are now going to bend inside. So the only difference is theta becomes minus theta. So if you look at just one equation, I'll look at equation 9. We have rho h, which is the effective density of one lattice here. Okay, and rho s is the density of the material that we have used to make this lattice. Then we have t, which is the thickness of the strut. We have h, which is the length of the vertical strut, and l, which is the length of the inclined strut. And again, our theta is the angle of the inclined strut. Okay, so these are given very how to get to these equations is explained very clearly by Gibson and Ashby. She has explained it very beautifully, and if someone is interested, it's just a very common book available online, so you can have that. It's Gibson and Ashby. Okay, so moving on. These are the constitutive equations for the structure that I'm talking about. I'm going to skip all these because I think the talk is going to get very lengthy. So just to tell in brief, this was my equation. This part is because of the shape memory alloy, because you can see here the familiar term sigma r that I talked about, recovery stresses. And this is our alpha delta T. Okay, and we have our Q matrices, which I said that we get matrices in case of orthotropic materials, and we have our temperature dependent. That is why I'm using this asterisk here. These are temperature dependent properties because shape memory alloys, as it expands, it changes its properties. Sorry, contracts, it changes its properties. And we have our strains at midplane, and we have our curvature at midplane. So this is just, I'm just running through it. And for the other layer, if it's a fiber layer, if it's a honeycomb layer or an auxetic layer, this is our equation, which is a very simple equation with our midplane strain and curvature, and then our alpha delta T. Okay, I solved these equations using FEM, and okay, so this is how I calculated and get ABD matrices. Just remember that in plates, when we calculate our stress resultants and moment resultants, we always calculate them at the midplane. Okay, if you cannot take everything from the stock, just take this from the stock, that when you are talking about composites, okay, they have multiple layers and they have different materials stacked on top of one another. We always take the material properties and the stress resultants and the moment resultants at the midplane, the geometric midplane. Okay, and then we have our final equations. These are the ABT matrices. When you come maybe in your fourth year, you'll be going through your composite courses, and you'll get more and more used to these equations. Okay, and these stress resultants and moment resultants are a result of our temperature dependent properties. Okay. And now I solve all these equations using FEM, and I validate them with my experimental model. So in our experimental model, this is when only one layer of shape memory alloy is reinforced, as I talked previously. We have a maximum of 45 mm of bending. And when I did it using FEM, I get 45.101 mm of bending. So here we have an average of 5. That's why I took it as 45 mm. And here we have 45.101 mm. And this T is equal to 66 degrees Celsius is where I get maximum amount of bending, which means that our shape memory alloys, they are in their austenite finish temperature. So they are in their austenite phase. Okay. So once we have validated the model, we build our model on different types of auxetic structures, which I explained. Here there are 2 layers of shape memory alloy wires. Here
Ma'am, ma'am, you are muted again.
am I audible now?
Yes, ma'am.
I have no idea how this is happening, but was the previous slide audible, this one?
Yes, ma'am. Till now, just 1 second back, it was
Okay,
muted, and then I was responding.
okay, then thank you for mentioning this. Okay, so yes, so here you can see that we have 2 different curvatures. So this structure that is bending, it is bending in 2 different directions. Okay, so this is a negative curvature, and this is a positive curvature, or vice versa. It depends upon what you are taking as positive and what you're taking as negative, as you guys must be studying in your moment courses, mechanics of materials in which you have moments. So one is positive and one is negative. So it's like a saddle. Saddle is what we put on our horses, no, to ride it. So this is a saddle shape, or we also call it something which has a negative Gaussian curvature. So the curvature, it has a positive one and a negative one, and when we multiply these both, we get a negative one. That is why it's a negative Gaussian curvature. Gaussian curvature is nothing but the product of the two principal curvatures of a structure. Okay. And then the final one, in which I had that auxetic layer that I was talking about. So one layer is of SMA inside, okay, and another layer is auxetic. And in this, we are getting this positive curvatures in both the directions. So this is also going positive. This is also going in the same direction. So we have a positive Gaussian curvature. And now you'll know why I'm emphasizing on zero Gaussian curvature, negative Gaussian curvature, and positive Gaussian curvature. It's because our torus structure is made up of three different curvatures. So now if we want to get that torus shape that I was talking about for the inflatable structure in space, the inflatable antenna experiment, we need a torus structure. And for that torus structure, we need three different Gaussian curvatures. One is negative, one is zero, and one is positive Gaussian curvature. So the zero one is very simple. The first one that I had, in which there is only one layer of shape memory alloys and it is just bending in one direction. Okay, so that is zero. Why? Because it has two principal curvatures. One is bending in one direction and the other one is just straight. So the other one is straight, and so the curvature is zero. So the multiple of that is overall zero. And for the positive Gaussian curvature, we have our dome-like structure and the other one which wasn't giving us a very good result. So the deflection was very little, which is not usable. So we have our dome-like structure, which we got from auxetic core. And then we have our negative Gaussian curvature, which is also required on the inside rim of the structure, which we got from our honeycomb core. So tying all this together, you can see the envision now that we have proposed to ISRO finally is this video. Okay, so we have do not confuse it with that now we are only going to use two layers of shape memory alloys. We are now going to use auxetic and honeycomb cores with it. This is just for the demonstration. So the idea is to embed the structure with shape memory alloys. If two directions are required, then two directions. If one, then one, and have honeycomb and auxetic cores. Then it is going to bend in first of all in one direction and then direction number two. So it is a small element. And then we join these two elements to get one very small element of the entire torus structure. And adding these multiple elements, we finally get our torus. So this is the plan. So this is why I was working on auxetic structures. This is why I was working on shape memory alloys. And this is how I was able to get an idea and a feasible solution for removing the gas from the inflation part and then controlling it only using shape memory alloys. I have done more work on the vibration control, which I'm not showing here, how adding shape memory alloys and actuating these shape memory alloys is going to change the frequency of the structure. I have done that work. I have also optimized the structure, as in how much shape memory alloy, the volume fraction of shape memory alloy required, and if the shape memory alloys have to be embedded at an angle in order to get a certain shape or size or certain amount of bending. So that also I have done, which I'm not sharing here. Another major application of these shape memory alloys is using them in these elastic metamaterials with a range of array of resonators. So these resonators, if they have embedded shape memory alloys, and then if they are actively controlled. So they are going to bend and then come back to their original position and bend and again come back to their original position. So when we actuate this part, when we vibrate this part, it will show us varying amount of frequencies. So these also have many applications, and tunable metamaterials using SMA reinforced composite resonators is one of the applications which I'll be working on in future. So that concludes my technical part. I hope that you guys were able to get a little bit of an idea about shape memory alloys and auxetic structures. Those were the two things that I was focusing on. And then people who want to know a little bit about fellowships and postdoctoral fellowships especially are welcome to continue this talk. So for the first thing that we need for a postdoctoral program is to find a supervisor. And how do you find a supervisor is, first of all, one way is networking. So either it is your network or your supervisor's network. And then he can or she can introduce you to some other professor, and they can then introduce you to someone else. So huge amount of networking goes into finding a host supervisor. The other way is to explore. This is the method that I used. So what I did was that I was going through these research papers, and at the end of these research papers, you have references, and the name of the people in these references are the ones who are working in your field. So just go through what department they are in, what interest they have, and what they are working on. So even someone who is looking for a PhD, this is a very good way to find someone in your field, is through going through research papers and then finding these professors through the references. Another method is just simple. Google them and just Google what country you want to work in, maybe, and then people who are working in your field of interest. So if someone wants to work in robotics, and then robotics also is, it's a huge field. There are many things that are happening in the field of robotics. So just make it very precise. What exactly do you want to work in? And then just search for professors working in that field. So once you have found your host supervisor, you need your some scholarship to sustain yourself. So there are two types of postdoctoral fellowship. One is project based. So what happens in project based scholarship is that the professor already has a project. So this is also for PhD. Okay, so someone who wants to apply for PhD. So you have a project which the supervisor already has, and then you apply for that project. There's a vacancy in that project, and then you apply for it. You're like that. Okay, I'll talk to them. My skill set is eligible, and they might be able to benefit from my skill set, and I might be able to benefit from their project. So you apply to those projects. And then other one is fellowship based. So you approach a host supervisor and you tell them that you have an idea to work on, and then you just need funding. So if you both can write a project together and then apply to an agency, funding agency, which can fund your project. So the other one is fellowship based. And then fellowships are also of two types. One is university based. Like in India, we have each and every institute has a postdoctoral fellowship, and PhD also has it. So one is university based and one is country based. Okay. So for university based abroad, you have to go to each and every university's website, and you'll have to see if they have a funding for PhD students, postdoctoral students, and also you have to talk to the foreign students department, foreign researchers department or foreign students department, and just email them and ask them if they have a fellowship for PhD or postdoctoral fellowship. Okay. The other one is country based. So there are some scholarships which are given by the government, and then they're a little competitive because then everyone is applying for them. And then once you get it, you can fund your project with it. So the university will get the money, and the university will then transfer the money to you. Okay. So these are some which I have compiled, and these are the top fellowships which I know about for engineering specifically. So I have not added any from medical field or humanities field. These are all from engineering point of view. So for US, you have Fulbright postdoctoral fellowship, and Fulbright also provides for doctoral research programs. So if someone is interested in research programs, there are doctoral research programs, and also for faculty, they also have some fellowships. So there is a faculty exchange program. Then just go for Fulbright website. They have a website, Fulbright Nehru Fellowships, and there is quite a great deal of detail to it on their website. The Indo-Shastri Fellowship and the Banting Postdoctoral Fellowships are available for Canada. And Indo-Shastri is also available after MTech or between MTech. So if someone is pursuing maybe integrated MTech among you guys, you can also look into research exchange programs, which are of 3 months. So if you're doing an MTech, you can go to Canada. And there are top universities which are affiliated with it, like the British Columbia is affiliated with it, Toronto is affiliated with it. And you can go for 3 months to explore and maybe do a part of your experiment there, which will also be a part of your thesis. Now, this is the one that I received. It is for entire Europe, which is a good thing. And it is also competitive, but because the funding is huge, because it covers the entire Europe, so chances are also high. So Marie Skłodowska-Curie Fellowship is for Europe, and all the EU countries are a part of it. And if you have a host supervisor in any of the EU countries, not UK because of the Brexit, so a host supervisor in any of the EU countries, you can talk with them, and you can write a project with them and apply for this Marie Skłodowska-Curie Fellowship. Go to their website. They have a very easy portal. You can just log in and then submit your details, and then it's done. Yes, so that is the MSCA Fellowship. Then for UK, we have the Newton Fellowship. It is for, I think, only postdoc, whereas Marie Skłodowska-Curie Fellowship, you can also search it for PhD. Then for Switzerland, we have Swiss Government Excellence Scholarship. This is very competitive because the scholarship number is very few. And someone who is interested in ETH Zurich or someone who's interested in EPFL can choose MSCA. So for Imperial College London, you have Newton Fellowship. You can look into that. And then for Germany, you might know about Humboldt Fellowship and Dart Fellowship. So Dart is also applicable for someone doing MTech. Okay, so there are exchange programs in Dart, which are both for MTech as well as PhD students. And Humboldt, from what I know, is only for PhD and postdoctoral students. So not for MTech students, but you should look into this. And then coming to India, we have Raman Fellowship, which is only specifically for ISC Bangalore. So if you want to do your postdoc from Bangalore, you have Raman Fellowship. And Aryabhatta Fellowship is again for entire India. There's also Inspire Fellowship for, we have Inspire faculty and other Inspire Fellowships for PhD as well. So that is also a part of Indian fellowships. So I think that that's it. And I have talked a little bit about smart materials and a little bit about, some smart decisions that you might want to make. And I'm not in any way encouraging you to go outside and do your studies outside. I'm just saying that if you want to do that, you should do that. I prefer to stay back and do my PhD here. But for my postdoc, I want to go outside because then the opportunities back home, they increase furthermore. So from that point of view, I would really encourage you to go outside, get more experience through their infrastructure, through their experimental facilities. But I will always urge you to come back and work for our country. So yes, with that, I'll conclude my talk. Thank you very much for your attention. And yeah, thank you.
Thank you, ma'am.
Yeah.
The students are requested to ask any question if they have in their mind. Ma'am will help you to clear your doubts.
Yeah. There is no need to, worry. Just ask any question. No questions are, worth not asking. Any doubt you have, any personal question, you can ask. Okay.
Hello, ma'am.
Yeah. Hi.
Yeah, yes, ma'am. Ma'am, you talked about the inflatable antenna, the dome structure.
Yes.
Ma'am,
Yes.
I wanted to ask that. So, like, suppose in a situation it is concave towards our side, and is there any way to make it convex, like to reverse it using it is in space, so there's temperatures and UV. You told about that. So, any way that we can modify it by ourselves?
Right now, it's a very good question actually, because it is possible that it can happen because yes, there is a lot of vibration there. But right now, no. In the inflatable antenna experiment that NASA did, they did not control the curvature, whether it's convex or concave. Neither are we looking into it. So in IIT Kanpur, the project was only focusing on the torus structure here. Okay, so the inflatable torus was what we were focusing on. But right now, no, and it's a very interesting query. And in order to make this successful, one should be able to control it. But no, right now they are not controlling it. Yeah.
Okay, ma'am. Ma'am, also I wanted to know about your journey from BTech to higher studies. Like, how can we do it so that we can benefit?
Yeah, see, in my case, I wasn't sure about PhD. So I took a 6 months break after my MTech. So my PhD is from December 2014 to February 2021. So I took, including the lockdown, I took 6 years and 2 months to complete it. And I wasn't sure about research. But the reason I got into research was when I was in my MTech second year, when I was doing my thesis, I saw that the flexibility that I have of the timing, it is far better than my fellow friends were experiencing in their corporate jobs. So it wasn't a 9 to 5 job. So that's why I was very much interested in research. Really, to be very frank, this is what it was. Now, research is actually a 24-hour job. So that I wasn't aware about. But you are happy to work for 24 hours when you are working for yourself. Okay, so that was my idea. So when I do research, I'm doing it for myself, I'm doing it for my lab, and I'm doing it for the betterment of the scientific community. It's not that I'm taking a corporate opportunity and uh, I mean, people who are okay with that lifestyle, good for them. But for me to to have these deadlines and these controls, it wasn't a very feasible method of working. So always try to figure out what will make you mentally at peace and mentally healthy. Okay, so if you are interested in that, in that corporate life, it's okay. But if you really want to, contribute to the field of science and, be a small part, teeny tiny part, because there are huge, scientists out there everywhere, but a teeny tiny part, even if you want to be of the scientific community, it's a great, very rewarding experience, I will say. PhD can be a little frustrating. Always remember that if you're thinking of research, because it's a long process. There are no deadlines, so you do not know where you are going. But as you're about to complete it, everything starts to fall into place. So you're everywhere, until your fourth year. All your data is somewhere, and you're figuring things out, and you're not in the correct direction. But as it starts to compile in the fifth year, you'll be able to see that your research matters, and you have done huge amount of contribution to this project. Okay, so my idea was to first of all get into a field which I can be comfortable in, which I can work on my rules. And the other part was that I was interested in studying. I really like to study all the time. So it's you just have to sit in a library and study, and then you have to go to the lab and do some experiments. So it's a very personal experience, this research. So that's how I went. But I hadn't figured it out right after that. I took a 6 months break, and I really focused on what I wanted to do, and also, do I want to do my PhD here in India or outside? So keep this in mind, because at least in US, in India, it is going to take you 5 to 6 years if you're in mechanical engineering. In IIT Kanpur mechanical department, the average is 6.5. Okay, so it is going to take 5 to 6 years. If it wasn't lockdown, it would have taken lesser time for me. But 6 years, there are many students who are in 6 years, but there are many students who have completed in exact 4 years as well. So it is 5 to 6 years. Okay, and 5 to 6 years, whether you want to spend it away from family and friends, and if you'll be able to manage it, very good, you can go outside and do it there. And if you think you won't be able to manage it that good for 6 or 5 years, then stay back and do it here. So these are my opinions on research and PhD. Okay, but be sure, before you get into research, be sure what you want.
Okay, thank you so much, ma'am.
Yeah, no problem. Any more questions? I hope these equations didn't scare anyone. Actually, these are very simple equations. Once you start working with them, no, they start looking very easy. So when I even started working with them, I was like, oh my God, why are they so complicated? So they look complicated, but once you come to know about what is happening inside, they are not very complicated. In fact, I think our 12th class mathematics was much more complicated than this. These are very simple equations. So need not get worried about anything that I have shown in my presentation. Okay.
Is there any more question? Ma'am, I think the students are a bit confused, so they are feeling shy in asking the questions.
No, don't be shy. Don't be shy. I mean, you have to ask questions to know more. Okay. Just ask random questions. It's okay. You can ask more about auxiliary structures. You can ask more about shape mineralize. And I will really encourage you all to go back today and watch some videos on shape mineralize and auxiliary structures on YouTube.
May I come in?
Yeah, sure. Yeah.
Ma'am, I would like to ask regarding the robotic fish, ma'am. And
Yeah. Okay. Here. Mm.
even if the means it is made up of some material like heavy material, how is it able to maintain the buoyancy inside the water?
No, it's not made up of a heavy material. This frontal part of the fish, it is all plastic. You see? It's all plastic. So it is actually floating on top. It is just propelling.
Is it like means is it like using the principle of like submarine where it is like able to maintain?
Principle of
Means how the submarine means float inside the water.
submarine. No. It's a very simple experiment. So they only have a plastic body here. So if you put something made of plastic, which is of such light density, in water, it is going to float. All they are doing is that they have this caudal fin, which is being actuated in left and right direction. Okay, just you see, it's just giving it a propelling motion in the front. they are not controlling the depth of the fish. Like in submarine, they do know they can go to deeper depths of the ocean and then they can come on top and then again they can dive in. That is not happening here. It is only floating and only going in the forward direction. So I'll just a second, I'll do this. You can see it more clearly. So it's a paper by Michael D. Bartlett. It was published in PNAS. PNAS is one of the very good journals in the field of physics, and it was published in 2017. So if you can write this down, you can search it, and they have also added more videos and more details to this research. So they have explained about what material they are using, what material they are using in the caudal fin, and how they are actuating these structures, how they are maintaining insulation inside water. So they have talked about all these things in their paper. It's a very good paper, actually. So the name of the paper is High Thermal Conductivity in Soft Elastomers with Elongated Liquid Metal Inclusions. So these metal inclusions, the sheet, sorry, memory alloys are the liquid metal inclusions. Okay.
Then how is it moving forward? Is it like flapping its caudal fin, or is it like
Yeah, you can see, no? Is my page being, can you see my page? Can you see the robotics? This caudal fin fish, can you see that?
yes, ma'am. Yes, ma'am.
Okay, let me explain more clearly. So the wires that you see here, no, inside, just a second, I'll use my laser pointer. So the wires that you see here inside, okay, the silicone, you can see those wires, right?
Yes, ma'am.
Yeah. So these wires, they change their shape when they are actuated. So they are giving it current. So by current, what is happening? That their temperature is changing. And when the temperature changes, the wire, they are changing its shape and they are going from left to right, left to right. And when the wire is going left to right by shrinking or by changing shape, the entire, so they are calling it metal inclusion. So the entire silicone, this caudal fin, it is also moving with it. So as it is moving in this particular, twisting like behavior, it is not exactly left and right. So it's a small twist there that is causing the propelling. So it's all the beauty of the shape memory alloys, which is inside this elastomer, which is causing it to change the direction and the causing the propelling of the fish. Is it a bit clear now?
Yes, ma'am. Now
Yeah.
I got it.
So yeah. The wire inside, it is changing the shape, causing the fin to change the shape instantly. See, it's flapping, and that's why it is going forward.
Okay, ma'am.
Yeah.
Ma'am, if you take the body of like something like of a very heavy metal, so
Uh,
maintain the buoyancy. So will means how can you provide the buoyancy? Means if you can provide some procedures.
Buoyancy, I'm not sure because I mean it is only for a basic demonstration that it can cause propelling. But for buoyancy, I'm not sure what they're going to do. That is why they use this plastic so that they do not have to worry about buoyancy and it can float easily. But no, I don't think that shape memory alloys its propelling is going to help with the buoyancy because see, the wires they get actuated very easily, but they don't cool down as fast. So they are good for propelling in forward direction, but they cannot maintain this buoyancy. But in the case like I showed previously, just a second. No. In this case, they have embedded shape memory alloys inside, and they can control the drag and lift. Now, if the same concept can be used for buoyancy, I'm not sure because they haven't done it yet. But they can control the drag and lift of the aerospace structures, airplanes. So these are the wings of an aircraft, which can be now used to actively control the drag and the lift. So maybe using this kind of a structure, they can also control the buoyancy and they can maintain a certain depth, even if heavy material is used for the manufacturing of the robots. It is possible, but it's not done yet, so I'm not sure.
Okay, ma'am. Thank you, ma'am.
Yeah, sure, no problem. Are there more questions?
Ma'am, I think there are no more questions.
Okay.
So, ma'am, we would like to thank you. It was a wonderful session. We hope
you.
that students were able to learn a lot today from this webinar. With this, we would like to conclude this session. Thank you once again, ma'am.
Thank you. Thank you for inviting me.
Ma'am, can we end this meeting?
Yeah,
with
sure.
permission?
Yeah, sure. Good night, everyone.
Thank you, ma'am.
Bye-bye.
Good night.
Good night.
Yeah.
Thank you,
Thank you.
ma'am.
Good night. Bye bye.